Okay, Unit 7 is kind of a strange unit. It's really forced me to kind of rearrange a lot of my lessons. There is a lot about Unit 7 that is review. C-Scope actually titles Unit 7, it's something to the effect of properties of two-dimensional shapes. Well, we've spent a great deal of time already this year talking about different two-dimensional shapes, triangles and their properties, and obviously quadrilaterals and their properties and things like that. Well, they're dedicating an entire unit to that, to those properties. Well, I'm not going to go back over, spend a whole bunch of time going over properties of shapes that we have already talked about. We'll review, a little bit before the unit is out, that kind of thing. But the only real shape that exists in two-dimensional space that we haven't spent a bunch of time talking about yet is the circle. And typically we've really kind of waited on the circles in years past in geometry. We've put circles until the end of the year, basically because circles have been a topic that, yes, it's something we're supposed to cover in geometry. We're supposed to learn the properties, but it has been something that has not been tested on TAX or on STAR. So yeah, we wanted to get it done, but we didn't really worry about getting it done before the TAX test got here or before the STAR test has gotten here. Well, this year the indication is that that circles will be tested at least to some degree on your STAR test. Okay, so we're going to have to go over the properties of circles, and this is kind of a weird situation because we're not anticipating very many questions about circles, but there are a bunch of properties about circles, so it's going to make us learn a bunch of stuff just in case they happen to ask different types of questions about them. So we're going to have to know, for lack of a better way of putting it, we're going to have to know everything. So the two, maybe three questions that might show up about circles, that we're prepared for those just in case. Okay, so this unit is going to largely be, as far as I'm concerned, about circles and their properties. But then when we do get to the test at the end of the unit, be prepared for the fact that you're going to see properties of all kinds of two-dimensional shapes, which means that if you didn't learn your Unit 6 stuff on quadrilaterals, you definitely need to go back and study that stuff and learn it. If you have forgotten properties of triangles and things like that, you definitely need to go back in your notes and look up properties of triangles and that kind of stuff, because it's all fair game on the Unit 7 test. Okay, but again, we're going to spend the majority of our time focusing on what is going on with circles. Okay, so we're going to have a bunch of definitions. As a matter of fact, it might not be a bad idea for you in this unit, or the way I'm doing this. I'm just going to call it the circle unit since we're not really doing what C-Scope says. You might want a page that has nothing but definitions. Okay, there's that many new terms and things like that for you. So you may want to keep all your definitions in one place, or maybe at the very least highlight them in your notes so you can spot them easily, especially for when you're studying. Okay. All right. First definition is a central angle. A central angle. And just in layman's terms, a central angle is an angle in a circle that has its vertex on the center and its endpoints on the circle itself. Okay. So here is what a central angle might look like inside of a circle. Okay. And if you want a statement to go along with that, then you would simply say angle ABC is a central angle of circle B. And please refresh your memories that we do use the 3-point naming system when we're talking about an angle. This is going to be especially important when we talk about circles. You're going to see that you are going to have a lot of angles, particularly around the center of the circle. So if you were to simply try to call this guy angle B rather than angle ABC, what you're going to find is that there's going to be a lot of angles that use point B as their vertex. Okay, so the 3-point system keeps us from getting confused. Okay. Now, obviously, a central angle intersects your circle at two places. those 2 points where the central angle makes contact with the circle, they become end points of what's referred to as an arc on the circle. Okay. Now there's that same circle from above. Okay, so you don't really need to write it down again if you've already got it. Okay. We catch a little new notation here. Okay, this little sideways parenthesis looking guy, or whatever you want to call it, little rainbow. Had a student once, they called it the toenail clipping. Okay, whatever you want to call it. Okay, when you throw that little guy over the top of back-to-back letters like that, then you are referring to an arc. This thing here on the left is pronounced arc, AC, and of course it is an arc of circle B. And probably the easiest way to think of and remember what an arc is, it is a fraction of the circumference of the circle. It's just a piece of the circumference. Okay. Now there is a direct relationship between a central angle and what is called its intercepted arc. Anytime an angle makes contact with a circle, it divides the circle into some pieces. Okay, the piece that is caught between the legs of the angle is called an intercepted arc. So there is a connection between a central angle and its intercepted arc. And that connection is this. The measure of the angle is going to be equal to the measure of the arc. And of course, by the symmetric property, you can read that thing backwards as well. The measure of the arc is going to equal the measure of the angle. So it's very easy to say that if you can figure out what one of them measures, then you will know exactly what the other one measures. Okay, and to put that in a diagram, okay, there's that same circle as before. The rule said that the measure of the angle and the measure of the arc would be equal. That's what this statement is saying. The measure of angle ABC is equal to the measure of arc AC. And the only other piece of information I have to offer you on that is the statement that both of these guys are measured in degrees. Now you're going to find out a little bit later on that there is a different way to measure arcs, but we'll talk about that later on. Typically, for right now, when we talk about arc measurements, they are the same as angle measurements in the terms that they are in degrees. Okay. Now, a little side note here on arcs. Well, it's not really a side note. It's actually some fairly important information about arcs. They come in many sizes, and it is those sizes that place them into one of 2 categories. Technically, I guess you could say there's 3 categories, but you typically only hear of 2 of these, but we will discuss the third one as well. There are minor arcs. Okay. Minor arcs are arcs that measure up to 180 degrees, which is to say they take up less than half of the circle's circumference. Okay. Minor arcs measure up to 180 degrees, less than half of the circle. Then, as you could probably guess, there are major arcs, which measure from 180 degrees up to 360 degrees, which in plain English would be to say they are bigger than a semicircle, but they do not form an entire circle all by themselves. Okay. And then there's this third little category that you're probably already familiar with, semicircle. Okay. If an arc were to measure exactly 180 degrees, we would not call it major or minor. It would be a semicircle. Okay. Not a whole lot more information for us here, but we do need a naming system for our arcs. When we are naming arcs, it is only necessary to use 2 points for minor arcs, but 3 points to name major arcs. 2 points for minor arcs, but 3 points to name major arcs. And I'll explain to you why the difference here in just a moment. Okay. I'm going to expand a little bit on that diagram from the previous pages. I'm going to add a new point into it, and I've just thrown a point D somewhere else out on the circumference of the circle. Now, hopefully when looking at this circle, even just with the very little time you've had to soak up the definitions of minor arc and major arc, I hope you can look at the circle and see a minor arc in this circle and also see a major arc in this circle. Okay. Well, very easy to say that arc AC is a minor arc. It very clearly consumes less than half of the circumference of the circle. The problem becomes this, okay? That arc uses points A and C as its endpoints. But the major arc coming to the left side of this circle, does it not also use points A and C as its endpoints wrapping around the left side? Okay, it uses the exact same endpoints. So if we were to call it also arc AC, how would we know the difference between arc AC that's going to the right-hand side of that circle or arc AC that's coming all the way around the long way of the left side of the circle? Because the naming system, you kind of think of it like it's lazy. It's not going to go the long way around the circle unless you make it go the long way around the circle. It's just going to try to cut the corner. So if you say arc AC like we have right here, well, it's just going to cut right across this short little right side of the circle. So if we want to say arc AC coming around this way, we're going to have to use 3 points. We're going to use A as one of the endpoints, C is the other endpoint, but we're also going to have to list some other point along the way so that our arc knows it cannot just cut this short side over here on the right. It's got to go all the way around the long side. Okay, so we'd say something like arc ADC to make that thing go the long direction. That's why it takes 3 points in order to name a major arc and only 2 points to name a minor arc. So you'll be able to tell if you're just looking at the names of arcs, you'll be able to tell if it's describing a minor arc or a major arc just based upon how many points it takes for them to describe the arc. If it's just 2 points, those are 2 end points and it's minor. If there's 3 points, then you got the 2 end points on the ends. A and C are still the end points, but because of that center listing in there, it's going to cause it to go the long direction around the circle. Okay. Another little piece of information, this one kind of fits into the common sense category. Okay, and we've talked about postulates like this throughout the year. The same holds true for arcs. Arcs can be added together or subtracted from each other in order to form larger or smaller arcs. And that's called the arc addition postulate or the arc subtraction postulate, depending on whether you're adding or subtracting. And that may be important for you to know that in the case of a proof. Okay, it's possible that you may have a proof about a circle, and in that proof they may be adding 2 smaller arcs together to make a bigger arc, or taking a big arc and subtracting something away from it to make a smaller arc. That's arc addition postulate and arc subtraction postulate. Okay. And a little bit of vocabulary that still holds true as well is the idea of congruence. If 2 arcs were to have the same measurement, then they are called congruent arcs. Okay, let's see if we can put some of this information to use. These are typical type questions, any of which might be fair game in a question dealing with central angles or the intercepted arcs that go with them. So I'll give you a moment to copy this down, and then we'll see if we can address some of these questions. Okay, the first question that is posed is just a simple identification. Name a central angle. Okay, well, who's got one? Angle what? BAC? Angle BAC? Absolutely. What else? Angle DAC? Absolutely. Endpoints on the circle, center on the vertex on the center. What else? EAB? Sure. More. Let me ask you this. I mean, there's a bunch of them. I think we're on to it by now. Is it possible that an angle we could name a big angle that might have two smaller angles inside of it? Like, could we say angle EAC, kind of skipping over line segment AD? I mean, is that an acceptable angle inside of there? Sure it is. Okay. Anywhere that we have any of those two line segments that make contact with the circle, okay, that's a central angle. Okay, so there's plenty of examples that are in there. We've just named a few of them. Okay. All right. While we're on the subject of naming stuff, let's name a minor arc. Okay, what's one of those? Arc ED? Sure, that'll work. Put the little rainbow or toenail clipping or whatever you want to call it over the top of that there. BC, sure. DC looks good, sure. Okay, and again, okay, you can skip over just like we had angle EAC. Could we put arc EC going past point D without listing it? Yes, we can. Why don't we have to list it? Because we are not looking at a major arc. It's just a minor arc, so all it needs is its endpoints. Okay. Okay. So again, a lot of different possibilities for minor arcs. Okay. All right, let's move on. Major arcs. Okay. Who can name me a major arc? Angle BED. Okay. B is an endpoint. D is an endpoint. It passes E along the way. And when you follow that route from B to E to D, does that consume more than half of the circle? Yes, it does. Okay, we could either tell it visually or by adding up the 120 and the 70 to get 190. That's bigger than half a circle. Absolutely. What's another one? Angle DCB. DCB. I'm not sure about DCB. It doesn't seem to make it more than halfway. Okay, but let's say we started at D, and instead of picking up, if we wanted to go DC, where would we want to actually stop? Maybe come all the way around to E. I think that would work. D, C, E. Okay, now you'll notice I didn't list every point that I came to. I didn't put arc D, C, B, E and put 4 points in there because it takes 3. 3 points to name a major arc. So I got the 2 end points and then any point along the way. Okay, what would be another? EBC, yep. Okay, and again, there's a bunch. We could probably come up with about a dozen examples in there of using those different endpoints getting a major arc. All right, and another thing we can of course be asked to do is to figure out measurements of different stuff that is inside of our circle. How about this one? What is the measure of angle BAC? This is kind of a gimme, isn't it? It's marked in the picture. The measure of angle BAC is 80 degrees. How about the measure of arc EC? Okay. What would be the problem with figuring out the measure of arc EC? Yeah. Yeah. We don't have all of the information that would be required, right? The arc addition postulate tells us that we can take this 70 degrees that we have and this measurement across there, add them together, and that would tell us what's going on with the angles. It would also tell us what's going on with the arcs, but we're missing part of the information. So what type of a strategy would we want to use to figure out what's going on with angle DAC in there? Well, what's one of the main properties of a circle? Start off and you take all the way 1 revolution all the way around, what happens? 360 degrees, 1 revolution around a circle. So we've got 120 degrees that we do know. We've got 80 degrees that we do know. We got 70 degrees that we do know. And we have an unknown value. And when you add that all together, that has to equal 360 degrees. We would be able to solve it very easily from there. Let's see what we have here. 360 equals 120 plus 80 is 200, and another 70 is 270. So the only thing to do to solve for x would be to subtract the 270 to the other side. And as it turns out, we were missing a right angle inside of there. Okay, so if angle DAC is 90 degrees inside of there, okay, what does that tell us about the arc EC, measure of arc EC? We have 70 degrees from here to there, 90 more degrees from there to there, so that gives you 160 degrees. There you go. Okay. Central angles are really very easy, very simple, straightforward to work with. You just got to learn a little bit of vocabulary, learn where your things are, and the math of them is really fairly simple. Okay, that's why we start off with the central angles. These are probably the easiest thing to work with in the circle. It gets more complicated kind of each day that we go. The formulas get more complicated. The math is a little bit tougher as we go, stuff like that. Okay, but for starters, that's the beginning of circles. Okay. So from there on out, we're going to have a worksheet, and that's the end of today.